This is the Smart Buildings Academy podcast with Phil Zito, episode 323. Hey folks, Phil Zito here, and welcome to episode 323. In this episode, we're going to be talking about understanding heating during shoulder months. So we'll talk about what a shoulder month is. We'll talk about different strategies for dealing with morning heat loads that then turn into cooling demands in the afternoon or late morning. We'll talk about the effect of environment on kind of a heating cooling strategy. You know, if you live in a humid area versus a dry area, your ability to influence heating and cooling loads is going to be different, and you're going to use different strategies. All right. So it's that time of year. You know, as I'm recording this, it's March 21st, 2022. And things are starting to get a little warmer. You know, I live in northern Arizona, so surprisingly, it's actually still quite cold. But I was in San Diego recently for spring break, and I will tell you that it did get quite warm outside. However, in the morning, it started off quite cold. So that can be an issue, right? You start off cold. You've got this cooling load this heating load. And then, you know, the sun comes out, you gain all this heat energy from solar gain. And next thing you know, you've got a cooling load. Why does this happen? And why is this an issue depending more so on where you live than anything else? All right. So if you live in an area that has humidity in the air, then you know that humidity, right, is moisture, and moisture is energy. Well, that energy, that moisture, as you learn, as you start to study things like heat transfer in this industry, heat retains much better in moisture and in water than it does in air. So we have almost no moisture in Arizona. Very, very dry. So at the nights, it's not uncommon, once we lose that solar gain, to see the actual environment drop from a 60, 70 degree ambient this time of the year to a 20, 30 degree ambient. We're talking dry bulb temperature. So with that drop, that is a huge loss of heat because there's no moisture in the air to retain the heat. So that delta between daytime temperature and nighttime temperature is quite substantial. Now, if you live in Louisiana, you live in Houston, you go somewhere like that, like if I were just to go here on my computer and type up weather, Houston, Texas, and I were to look at it, I would see that the drop, right? It's 73.50. So we're looking at a 20 degree drop. And if I were to look at temperature, Prescott, Arizona, I'll see that there's a 30 degree drop between where I'm at. So that is a substantial difference in temperature, right? You go from a moist area, you can drop 20 degrees overnight. But in a dry area, you can drop 30 to 40 degrees overnight. So what does that mean from a shoulder month perspective? And what are shoulder months? So shoulder months, depending on where you live, are typically February to April, right? And September to November. And those are months when you are still in the previous season's primary mode. So that February to April, the previous season's primary mode would be heating, right? So November to February is heating season. Obviously, if you're like in Wisconsin or in Maine, then it's a substantially longer heating season. But on average, November to February is a pretty solid heating only month, and then using free cooling if you absolutely need cooling, and then unitary cooling for your process loads being things like data closets, etc. Now you look at the September to November, and that's the shoulder months from the previous season, which is a cooling scenario. So, from April to September is traditionally cooling season. You don't tend to run heat. Now, the issue comes in this shoulder month scenario where you start off maybe in the case of here where I live, 38 degrees, and by 3 o'clock, you're 68 degrees. Now, why is that? That is because where I live and where other people live that is a similar environment is a dry environment. And a dry environment, as I mentioned earlier, has no moisture in the air. Moisture retains heat energy in the form of humidity, right? So that's why oftentimes if you get more advanced in your outside air control strategies, you'll be looking at enthalpy, which is heat energy, and or you'll be looking at the difference between outdoor and return enthalpy. And you may make a decision that there's less heat energy, less moisture in the return air, thus it's easier to use mechanical cooling than it is to use outside cooling. All right, so what happens with this scenario here is we start off, and you're welcome, Chris, we start off with this heating load. And I'm going to talk through the dry scenario first, and then I'm going to talk through the more humid scenario next. So we start off with this heating load in the morning, and you're running heat, you're running heat. And then we have the solar gain. Now, depending on where your building's facing, and depending on time of year, you could get more or less solar gain. So for example, the place where I work has a eastern facing block of windows. So in the morning, the solar gain is quite significant. There is a really quick solar gain and solar heat to the exposed spaces. Why is this important? Because the lower level, the non-exposed spaces, do not experience that solar gain. So they actually stay quite cold. And so now you run into this weird scenario where you have one area that has a heating load and one area that has a cooling load. Now, how do you deal with this? Well, the first thing you need to be cognizant of is this concept of preheat, of kind of optimum start, morning warm up, whatever you want to call it. And it's this concept of running the heat till you get to a stabilizing load or stabilizing solar gain. What do I mean by that? Well, in a really dry scenario, you're not going to be retaining heat. So the idea of heating and then you're warming up the moisture in the air and then it's going to just retain and you're going to hold heat, that's not going to happen. If you run heat in a dry environment before sunlight and you turn off that heat, you're going to real quickly lose that heat as you introduce new fresh air, because remember, for buildings, we have to introduce fresh air. So you're going to want to hold that heating until you get enough solar gain that you start to go and heat up those spaces. And I tend to find that, that depends on glazing of windows, tinting, etc. Like I said, where the building's facing. But I tend to find if you're an eastern facing or southern facing window base, you will tend to go and become semi-self-sufficient depending on the temperature in a shoulder month right around 10, 11 o'clock. That's where you'll start to see that the areas exposed to solar gain are going to start to maintain temperature. You could turn off the heat and you can switch to what? Ventilation mode. Now, when you switch to ventilation mode, you do need to be cognizant that depending on outside air, you could actually still have to run the heat a little bit longer. But most of the time you can switch to free cooling or ventilation mode. There is a difference between free cooling and ventilation mode. Free cooling is we are trying to meet a cooling load. So we're above set point for our space. We're introducing cool air to cool down the space. Ventilation mode is we are simply circulating air to meet our ASHRAE 62.1 standard, of which, your required minimum ventilation based on space type, based on occupant density. So we have that. And then we will tend to see that the solar gain will overpower our retained kind of temperature within the space right around 2, 3 o'clock. That's when we get the most solar gain, and we will start to have to kick on cooling until the end of occupancy period. So that's one kind of generalized basic strategy for maintaining in a non-humid environment. Now, another thing to consider are what are things you can do? Well, if you have, let's talk about a typical square envelope of a commercial office building, glazed windows all around, and you're getting solar gain on the east, but on the west, you have no solar gain and you have no humidity really in the space except for what you're potentially introducing, then you're going to run into a stratified airbase. You're going to have stratification where you have cold air on the western side and you have hot air on the eastern side. And the same with north-south, right? And that ebbs and flows based as you move closer to summer, depending on where you're located in the United States or in the part of the world, right? The sun's going to shift. And so you may get more exposure on the south. You may get more exposure on the east. You may get more exposure on the northeast, depending on what goes on. But I want you to think about this. If you kind of follow my finger here, for those of you who are listening to this in the podcast recording, you can't see my finger, but basically you follow the sun across the sky, and that's where that solar gain is coming in. And that is going to be your primary heat source. Now, yes, there is respiratory heat that is put off by people. A good explanation of respiratory heat and so gaining that, for the life of me, I always get sensible and latent mixed up. Gaining latent heat, if I remember correctly, which is going to be heat that kind of remains, and then sensible heat is going to be like direct heat. So from like a heat source. I may have these mixed up. I always get them mixed up because you can simply Google latent and sensible. That being said, when you need to consider heat load from people or processes, you want to consider ASHRAE 55. ASHRAE 55 will talk about the aspect of respiratory heat gain, of the effect of airflow on the human body, etc. So how can you deal with this need for cooling while not subcooling your space in a heated scenario? One way you can do that is increasing airflow without increasing cooling. So it's well known in non-humid areas that if you can get into a shade, like a place where you don't have the solar gain, and you can increase the ventilation, the airflow across the human body, the evaporative effect will take effect, because remember, that's how humans reject heat, is we sweat. That heat comes out in the form of moisture, and the air flows across that sweat, that moisture evaporates, and that evaporation state change produces a lot of heat reduction. So simply by increasing airflow, whether that's through fans, ceiling fans, whether that's through increased discharge, that's why I talked about a ventilation mode, so that'd be discharge airflow, etc. If you have the fan capacity, are going to have a much lower cost speeding up your fan than you are kicking on your cooling system. So in those initial shoulder months in a dry environment, your best bet is to go and actually simply increase airflow, which will give you that evaporative effect, which can satisfy that human desire for cooler air. And you'll notice that if you study ASHRAE 55 and you study the thermal comfort corridor, as you get to a lower relative humidity, you can have a higher dry bulb temperature. So you can have a higher dry bulb temperature and a lower relative humidity, but as we transition this discussion to a more humid space, you can't really take advantage of that. All right, so now let's talk about scenarios where you are in a moist environment. So as I mentioned a little bit earlier, there's kind of two environments we're controlling to. We're controlling to either a drier environment or a moist environment, a humid environment. Humidity actually can somewhat help in your heating months or in your shoulder months on the heating side, not so much on the cooling side. But on the heating side, it can help because remember, moisture retains heat. And if you've ever been in a moist space, you feel muggy, you feel warm. So people can feel more warm with humidity. So you can heat up your space, and then depending on the relative humidity, you'll actually retain heat within that space longer. Now, I mean, there's a lot of factors that come into this. There's insulation factors. So the amount of insulation, type of insulation. There is the pressurization factors. Is this a positive or negatively pressurized building? There are factors to consider around, has any objects within the space retained or lost heat? Concrete floors with metal cabinets are going to hold a lot less heat than, wood and carpet and stuff like that. So you need to be cognizant of the interior. But if you can preheat that space, it will retain heat longer. So whereas in the dry environment, you have to keep heating until the solar gain comes, in a more humid environment, you can heat and then you can just go to ventilation mode quicker. Usually, by like 9 o'clock, you'll see a pretty big swing. And then as you heat up that space and you've retained that heat, now you move to ventilation mode. But the issue now becomes humidity because, right, as air gets warmer, that relative humidity is going to increase. The relative humidity is going to decrease, but the amount of moisture that can be retained by the air as it gets warmer is going to increase. That's what I meant to say. Is if you've ever looked at a psychrometric chart, it kind of is an up-facing curve, and that curve that is increasingly going up is the amount of grains of moisture per pound of dry air. And so as you move to a higher dry bulb temperature, you're able to retain more moisture in the air. That's why we subcool air to remove humidity. We bring it to dew point, then we subcool it. So we bring it to full saturation, subcool it, wring out the air, and then warm it back up, and it is drier air. The issue with warming air up potentially is that you can allow for more moisture to be in that airstream. So now we've got a potential humidity issue in these scenarios. In addition to that, you're going to need to work mechanical cooling more in a humid environment than a dry environment. So what we want to be aware of is that we're going to be able to use free cooling not necessarily as much in a humid environment. So that humid environment is going to have more moisture in the air. It's going to have more enthalpy. So and obviously as it's colder in a humid area, you tend to have more relative humidity. All things being equal, as temperature decreases, relative humidity tends to go up. As temperature increases, relative humidity tends to go down. That doesn't mean that the amount of moisture in the air is less. It can actually, 30% relative humidity at 90 degrees can be significantly more than, 45% at 60 degrees, 45% relative humidity at 60 degrees. So you want to be cognizant of that. So how do you deal with that? How do you go and deal with that scenario? Well, this is where you're actually going to take advantage of the moist air, and you're going to go and actually kick on cooling sooner. And the sooner you can do it, the quicker you're going to keep the humidity out of the air. By keeping the humidity out of the air, people aren't going to feel as moist and hot and sweaty. The evaporative effect is going to take advantage. You're going to be able to take advantage of the evaporative effect, and you're going to be able to go and cool people down easier. So I know there's a lot of not math, but science in this discussion, and I kind of went super high level on it. There's much deeper science in this. But what I want you to take away from this is that in the shoulder months with heating, and we're not going to do another episode. We'll just talk about it here. In the shoulder months with, the heating load, you're going to have to go and heat up the building in the morning. Some ways you can go and mitigate this heating load, as I mentioned, is by going and implementing better insulation, implementing better window glazing, window shades that allow solar gain through, and then close down to reduce solar gain once you've satisfied the space. That is a great way. Do remember, though, that in drier environments, because there's no moisture in the air, the heat retention is going to be less, so you're going to have to run the heat longer. But the benefit is the heat's going to disperse faster, so you're going to have to run the cooling less. Whereas in a moist environment, you're going to have to run the heating less because the moisture is going to absorb the heat, but you're going to have to run the cooling more because you're going to have to remove that moisture in order to keep the relative humidity down, because that moisture is going to contain heat energy. So I'd love to hear from you. Did this help you better understand what's going on during the shoulder months? Did it help you better understand kind of how heating works and how cooling works? I'd love to know from you. Let us know in the comments. And if you have your own strategy for controlling heating and cooling loads during the shoulder months, I'd love to hear from you about them. Thanks so much for being here, and I look forward to seeing y'all in a future podcast episode. And as always, let us know anything you'd like to hear about, and we'll make sure to incorporate it into future episodes. Take care.